Hello Internet, my name is Quinn and this is Blondihacks. This is part 2 of the lathe-only engine build. Hopefully all of you new folks that just got lathes are following along and you can build something actually kind of fun with your new lathe instead of just a bunch of bushings. Today we're going to build the cylinder and the piston, so let's go. Here's the cylinder we're going to be building. The piston bore is a blind hole, which is a bit unusual. Steam engines, even simple ones, typically have an open cylinder bore with a cylinder head at one or both ends. But I've, as I said before in this series, tried to simplify this engine as much as possible, get the part count as low as possible to make it as easy as possible for a beginner to build. For that reason, it's also a single-acting engine. Double-acting wobblers do exist, but they're uncommon. Most of them are generally single-acting because, again, the goal of these engines is not to be as efficient as possible or make as much power as possible. It's just to make something that runs and is fun to make. Starting with brass round bar, the decision you'll have to make is, will this brass round bar fit through your spindle bore? If it doesn't, you'll have to start with a shorter piece, and this can be a little bit trickier because depending on how deep the jaws on your chuck are, you may not have a lot to hang on to and still have enough stick out to get all of the features done in a single setup, which is important in this case. But you can do it if you need to. If you can use a longer bar, it is easier, so that's what I'm going to do. So I'll dial this in now, and I'm dialing it in even though it's still rough stock because I want to remove as little material as possible. The round bar that I happen to start with is very close to the final dimension of the cylinder, and that final dimension of the outer part of the cylinder is actually fairly important, more so than usual for a steam engine. You'll see why in a minute, but I'm going to start by facing off the end, as is tradition. With most steam engines, you want the ends to be as square as possible to the bore, so you do them in a single setup because generally the cylinder is mounted at one end to a frame or a steam chest or some other contraption, and you want that bore to be running square to whatever it's mounted to. Interestingly, for wobblers, that doesn't actually matter very much because the cylinder isn't attached to anything on the ends. Now, as I said earlier, I'm taking a very, very light initial cut, just basically a touch off, and I'll see if that managed to clean it up. And it looks like it came close, but not quite, so I'll just move in like a tiny amount, 1 thou and a half, 2 thou, something like that, and take another cut. The next size up of bar stock that I happened to have on hand was way too large, and I was going to have to turn a lot of brass into chips, and I hate to do that if I don't have to, so I started with this bar that was only very slightly larger than we need. But as I said, the outer dimension of this cylinder is important, because it's a reference for a very important cut that we're going to be making shortly on this cylinder. Before we do that though, we're going to do the bore, and we're going to do the bore in this same setup. And that is also important because for this particular engine design and for the order of operations I'm showing, the bore and the outer dimension of the cylinder have to be as concentric as we can get them. Again, more on that in a second. The first step then for the bore is to pilot drill it, and we need a very accurate drilling depth. If you look in the drawings, you'll see that I've actually marked the end of the drill cone for the pilot drills in that drawing and dimensioned that so that you can see exactly how deep to drill, because obviously we don't want to break through the virtual head at the top of the cylinder. I'll do this by setting the end of the drill up against the end of the work with a feeler gauge so that the drill isn't going into that center that we drilled and creating some random amount of error there. Once I've got a light drag on that feeler, I zero my coil DRO right there, and then I advance the coil DRO by the thickness of that feeler and zero it again. And now I know the tip of that drill cone is right on the end of my work. You don't have to have a coil DRO for this. If I didn't have one, which I didn't used to, I would do this sort of thing with a dial indicator set on the end of your quill. Works just as well. I don't typically use the quill hand wheel markings for something like that because lathe quills tend to have a lot of backlash in them, and it's very difficult to get an accurate reading there. So when drilling depth is as important as it is here, we don't have a lot of margin for error at the end of the cylinder, then go ahead and use a dial indicator or a DRO. Next, I'll come in with a larger drill. We're going to get that close to final dimension. We want to get within reaming and or boring range. So again, I'm using the feeler gauge because I don't want the end of this drill to go past the end of the cylinder either. And in we go with the big drill to get rid of most of the material for this bore. To finish this, like any piston bore, the two most important things are dimension and geometry of this hole. Drills don't make round holes, they make three-lobed holes, so we need to make that hole round first of all. There's two ways we can do that. We can either ream it or we can bore it. Boring is better if you have a boring bar small enough to get in that hole, because boring will correct any concentricity error introduced by that drill. If you're not drilling very carefully, then you've likely lost concentricity. The reamer will dimension and correct the geometry of the hole, but it won't correct any concentricity issues that the drill created. Now, that said, I have built two of these engines with a reamer, and honestly, it works fine. If you're careful drilling, this engine is fairly forgiving in that way. This time I am going to do the boring bar. My boring bar will fit in there, but it doesn't have enough depth, so I'm actually going to do a hybrid. I go in there with the boring bar as far as I can, but I'm stopping short of final dimension, as you can see. I'm a few thousandths short there. That's a really good fit, just verifying where I am. No, you stop doing this and get on with the video. Then I'll come in with the reamer and finish that out to dimension. Because I've bored the outer section of the hole, the reamer is going to remain concentric, being guided by that bore, and then once it gets to the bottom where the last little bit of it is still only pilot drilled, the reamer can dimension that, and it's going to stay concentric because it's been guided in by the good part of the bore, if that makes sense. Let's see how that reamer did on dimension. Yeah, the nominal size gauge pin, oh, it's tight. It kind of wants to go in. Let's go down one size. So going down one size, it's actually a tiny bit loose in there. There's a little bit of play in that. So I think that reamer actually cut a few tenths undersize because it's definitely halfway between those two pin sizes. I'll try the big one again. Yeah, it's like, it would probably push in there if you tried hard enough, but I might have trouble getting it out, so I'm not going to. So that reamer cut a little undersize, which stands to reason when you look at what I paid for that reamer. However, this is a good teaching moment because this is why you always do the cylinder first and the piston after, because it's much easier to fine-tune the fit of a piston to a cylinder than vice versa. I tried to show you the finished bore, how there's kind of a drill cone at the end and a full dimension bore right up to that drill cone, just like shown on the drawing, but unfortunately the camera doesn't really show it, but it looked neat in person anyway. That's all we need from this setup, so I'm going to part it off now a little bit over length so we can face it down to final length and make sure the top of the piston looks nice. Random pro tip, chopstick in the tailstock, excellent work catcher. And Yahtzee. That is looking good. Now the next thing we need to do is face that down to final length. This is where we will find out if we did all of that precision drilling accurately or not. I have not bothered to dial that in because it doesn't matter for a facing cut. That's why you see it wobbling. I take it down to final dimension, and luckily we didn't break through into the bore, so we know that our drilling was accurate. It's always a really sickening feeling when you see that hole appear as you make that last cut, but that went perfectly. Now we need that flat side that I talked about, and this is the valve face of the cylinder. This is probably the most critical feature on this part. We're going to do it in the 4-jaw chuck by holding it sideways. If you have a milling attachment for your lathe, that is actually an easier setup for doing this, but we can do it this way. I've got shims in there to protect these finished surfaces. The main thing we need to make sure of is that the cylinder is sitting square to the lathe. Lathe chuck jaws are not guaranteed to hold things square. They're usually pretty good, but it's not guaranteed. I've got an indicator with a wide flat tip on it that can ride on the high spot of the curve. And you can see it's about 5 thousandths crooked. So I'm going to tap that straight now. This is important because this face that we're creating needs to be parallel to the piston bore as accurately as we can. Otherwise the piston may bind up because of course the piston wants to run straight up and down, but the cylinder would be mounted crooked on the frame if this face isn't parallel to the bore. That looks good. This would be better done with a dial test indicator, but I don't have any dial test indicators with tips that are large enough to ride on the top surface of the curve. I'm ready to make this cut now, and the next most important thing is the touch off. And this is where the concentricity of the outer and inner dimensions is critical, because We're referencing the cut that we're going to make from the outside of this cylinder, but the dimension that actually matters is the distance from the center of the bore to this surface. That's what's dimensioned on the drawings because that's what's important. So in order to achieve that, we do a very careful touch off. I moved in until I just saw the first wisps of a chip on the outer surface of that cutter, and then I zero my DRO there. I could do that with an indicator on the carriage as well, and then I can start moving in and making passes until I've removed the exact amount that the math says we should remove. You got to be careful here because we're doing an incremental cut that needs to land on an exact dimension that's absolutely determined from the other direction, from the bore to this surface. If we were doing this in a mill, then we could indicate on the bore and then translate up from the bore and measure that directly. But because we're in the lathe, we don't have access to the bore, so we have to do this measurement indirectly. But that seems to have gone just fine. Let's get that out of there, see how it looks. And yeah, that looks excellent. We can measure that now and verify, and we did in fact nail that. Now, a little editorial note here. If you're paying close attention to the drawings, and to later in this video, you will notice that this flat spot you see right here is shallower than what you will see later. That's because I'm literally doing R&D on this engine also as I film it. So I found later I had to adjust the dimension of this flat face a little bit to get better valve sealing. I did that by making this cut deeper and thus making the flat surface wider, and I compensated by thinning out the crankshaft web at the other end of this assembly. As I was developing this engine, I was trying to keep this surface as shallow as possible because it makes the next two holes that we're going to drill a lot easier to do if this surface is shallower. But the engine wasn't going to run well as shown here, so you'll see this surface magically get deeper later on. I just set it up in the lathe just like you saw and cut this surface again. The drawings, by the way, are correct, so if you make it to the drawings, you will end up with the modified dimension that's going to work correctly. To the layout bench now to lay out the two holes that we need to put on this flat surface. I'm going to do this on the surface plate by first finding the center line. I get that vertical surface, I guess, and then I'll touch off on the top of the cylinder, move down by the radius of the cylinder, another instance where that diameter is important, and that'll allow us to scribe the center line right down the middle of that flat surface. Again, making sure that it's being held vertically in that V-block. And then from here, I set it down on the surface plate on one end, and I mark the locations of the center pivot hole and the valve inlet hole at the top of the cylinder. Those will get center punched, of course, as well, and then we'll go over to the lathe and drill those out because, in particular, the cylinder pivot needs to be as square as we can get it to this flat surface so that it will pivot smoothly and not bind up. This next setup is probably the most complex one on the engine. It is tricky to do this, but we can't do this on the drill press because we need as much squareness as we can get. For the short axis, I squared it up with a precision square and a light, referencing my cross slide. That'll be accurate enough for this dimension. Then for the long dimension, I went to the dial test indicator, and I'll dial it in similar to what we did with the regular indicator before, but now we have a flat surface, so it's easy to use the DTI, and we can get it more accurately straight in the jaws. Next, I dial in the punch mark so we can center that up and drill that hole. And of course, dialing in the punch mark probably affected one of those two squareness measurements that we just established. So once you've dialed this in, you got to go back and check squareness on both dimensions again. Typically one of them has moved. In this case, the long axis did move a little bit, and I had to do a little tapping once again on that to get that dialed in. And you'll typically have to go in circles a little bit until everything is dialed in and nothing has moved. This is a time-consuming setup, as I said, but it is important. Then from here, it's a matter of doing, again, a very accurate drilling and reaming operation using the feeler gauge to get the exact depth because, again, there's not a lot of wiggle room here. If you go too deep, you are going to break into the bore. A quick note on that setup, that was a lot of work. There is another way to do it that I tried on a previous iteration of this engine. What I did was I set up the flat spot cut with a center punch already established on the outside of the cylinder. So I centered up the punch mark and the round cylinder at the same time, and then I made the flat cut and drilled this hole in a single setup without moving anything. And that absolutely guarantees perfect squareness of those two features. However, that setup was actually a lot more difficult, I think, than this layout method, because it's actually quite difficult to ensure that a punch mark on a cylinder is not just centered, but also in the outermost orientation on that cylinder. Otherwise, this cross hole is going to be off axis on the cylinder bore, which would also be a bad time. So it's 6 of one, half a dozen of the other. Which of these two setups is easier, but I think I like this method better. Next is the valve port, and I opted to do this on the lathe because I was kind of here and set up anyway. All I had to do was recenter on the other punch mark. However, this doesn't actually have to be perfectly square like the pivot does, so you could easily do this on the drill press and it would be fine. In fact, you might have to, because you can see I've got a lot of jaw sticking out on one side, so this amount of offset, depending on the size of your chuck, may not be possible. You want to make sure you have at least 3 chuck jaw threads in each chuck jaw, otherwise you risk that jaw coming loose and flying off. You can imagine what a bad day that must be. To be clear, I've never seen that happen because I am careful to make sure there's at least 3 threads engaged on my chuck jaws, but it's easy to do by accident, I'm sure, so be careful with that. Oh, you may have also noticed the shims on the end of the cylinder changed in the middle of that last setup. With those thick copper shims, I was having trouble getting the part tapped in straight, and that sometimes happens with thick shims. That's why I also don't like jaw covers on the chuck jaws for small parts like this. Thin shim material works better because the thicker material can influence the squareness of the part in the jaw, and you may never be able to tap it in straight. What'll happen is you'll get it straight and then you tighten the jaws all the way and it goes crooked again and you can never get it straight. Anyway, onto the pivot pin, which is a very simple piece of drill rod, face to length, thread put on one end, Bob's your uncle. Very simple parts, why we use drill rod for that, makes this engine much easier to build. There's the finished cylinder. We'll do a test fit now with that pivot pin in place. That pivot pin hole, by the way, is reamed because I want a snug push fit on this pin. That pin is going to be Loctited in place. Here now you can really see the importance of squareness for all of these features because we've got 2 large surfaces that are rubbing on each other, and if they aren't parallel and being held parallel by a square pivot, that's not going to work. That's moving well. It's a little bit tight, so I'll put a little bit of emery on that pin just to make that run smoothly. We want this to be a nice, easy running fit. There shouldn't be any play in it, but it should be easy to swing back and forth. Otherwise, we're just going to be wasting a bunch of power dragging that surface back and forth. But that looks good. Then on the back of that pivot, there's a spring and nut assembly that allows us to adjust the tension of that joint and also increase the tension as the surfaces run in. The more you run a wobbler, the more those mating surfaces will run into each other and the seal will improve itself over time, and you can adjust that tension as needed. Let's check the port alignment now. As we swing over to the exhaust side, you can see those line up perfectly. Sorry for the camera parallax, but those holes lined up beautifully. And then for the intake port, this one's a little harder to see because it's inside the frame, but we can shine a light up through the cylinder and you'll see the intake on the top of the frame light up when those ports align. And I will say these port alignments don't have to be perfect. The very first engine I ever built was a wobbler similar to this, and my ports were misaligned by about 50% because I was terrible, but the engine still actually runs great. It's not very picky. Onto the piston now. We'll start with a simple piece of round bar. This is a very straightforward turning job. It's a long, thin part with a bunch of features that we want to all be concentric to each other, so we're going to do this in a single setup. That means facing it, putting a center in it, pulling it out, and using tail support. The one slightly unusual thing you'll see me doing here is I'm going to do this whole thing with left hand turning because I want the piston at the tailstock end. There's a couple of reasons for that, which we'll get to. I'm going to leave extra material at the tailstock end because I don't actually want that center drill left in either end of my part. So you'll see how I achieve that here momentarily. But I'll start by turning the whole bar down to the outer dimension of the largest diameter, which is the piston itself. And this is, of course, the critical diameter on this part. A piston to cylinder bore fit is very important in any type of engine. The exact fit depends on a lot of factors. In this case, this is an engine that's going to primarily run on air, but I want you to have the option to run it on steam, and importantly, it does not have rings. So it needs a little bit more generous clearance than, say, a straight air engine would, but not as generous as a ringed piston engine would have because it doesn't have the benefit of rings to create a good seal. and I wanted you to be able to run it on steam if you want, so we need a little bit of expansion range. If you make a ringless piston suitable for an air engine, such as is literally inside your air compressor, then that will run beautifully on air, but if you run it on steam, when everything heats up, it's going to lock up. You'll note in the drawings, this is the only pair of dimensions that have actual tolerances specified on them because this is critical. I've set a hard floor on the bore size, and I've set a hard ceiling on the piston size to make sure there's a minimum tolerance in there that will run reasonably well on air or steam, or whatever other compressed gas you might like to try. Also of note here, I did not start by cutting a groove at the left end of the part, which for left-hand turning you normally want to do so that you have a place where you can push the tool in and start your next pass. However, this is brass, so we can just shove the tool into the work directly and make a path as we go. But with something tougher like steel on a part this small, you're not going to get away with that. It's going to chatter like crazy. You can't just shove the tool straight into the work. I'll check the dimension out here where the piston is going to be. And, oh, look at that. That is dead nuts. Very happy with that. Now for reason number one, why I intentionally turned it with the piston facing the tailstock, because right at this moment I can pull the tailstock out and we can test fit the cylinder and double check that that fit is good. That should slide on there easily. The tiniest little bit of wiggle is good. There should be some movement in there, and it should be very, very free spinning. So that is an excellent fit. Very good. Once that's at diameter, I'm going to put a rough mark on the end for the length of the piston, plus extra at the end so we can remove that center mark. And this layout line is pessimistic, so I know I'm short of the dimension because I'm just roughing in the shape of the connecting rod and the connecting rod end at this point. The connecting rod end is my next largest diameter. Then I measure what I've got left there, and I'll finish this to an accurate length for the piston plus a fixed amount of 200 that I've left at the end for the center. Now I'll come in with a grooving tool and form the shoulder at the top of the connecting rod end, and that'll also give me room for the turning tool to come in and turn the connecting rod down. The functional purpose of the connecting rod in this engine is actually just to lower friction against the crank web, because if the entire piston rod was full diameter, you'd have a lot more surface rubbing on the crank web as the engine turned. Once that's done, I'll do a quick sanity check before I part off to make sure that my dimensions all look correct. If I need to make any changes, now is the time before I part it off. And yeah, just making some sanity checks. Everything looks really good there. So in with the parting blade, and we will Yahtzee this thing off. Here's another piston fit test you can do. The piston should drop right in under its own weight, and you'll see right at the bottom, there's like an air spring deceleration effect. And that's where the piston has blocked the port and is now only allowing air to escape around it. And it should allow some air to escape. You don't want it to be a perfect airlock at the bottom, because then that engine is not going to run very well, and especially if you run it on steam, it's going to seize up. Reason number two that I left-hand turned that, I can now hold it in a collet and face off that center. Because the piston is the largest diameter, it's trivial to hold the part by this diameter at the end. With that faced down to the correct length, that is our completed piston. Almost. We still have one more thing to do, and that's drill the cross hole for the crank pin. Now, this could be tricky. You could use something like a cross-drilling fixture if you have one. I made this one years ago, but it's too big for this job. There are also lathe cross-slide cross-drilling fixtures that you can get. This is a kit from Hemingway for doing that. There are also ones that people make for their lathe tailstocks. Lathe tailstock cross-drilling fixtures used to be a very common model engineer project because you always need to do a lot of cross-drilling on small parts. However, if you have none of those options, I'll show you a simple way to do it on the drill press with nothing more than a humble steel block that has been bandsaw cut to be reasonably square. This doesn't have to be machinist square. Woodworker square is fine here, but if you want to square it up in your 4-jaw chuck, you certainly could. So I've got layout die on 3 corners, and what we're going to do is make a drilling jig for this cross hole. I'm going to set my height gauge at an arbitrary height such that the end of the part will fit in the block, and I'll scribe that same height on the other side. Then turn it 90 degrees, and again mark a random line where the part will fit in the middle of the block if we drill that. And again mark that on those 2 sides. And then the one dimension that really matters, on the top, we want to go up the distance from the end of the feature to the center of the hole. This is what's actually going to set the hole position on the part. So we'll use the height gauge to do that accurately. And then of course we will center punch all those, and we'll go over to the drill press and drill these out. Again, I'm aligning all of these with my center finder and my float lock vise, but there's other ways to do this. You could use a wiggler, for example. These are straightforward drilling operations. We'll drill a pilot drill and then a nominal diameter drill to hold the part. This needs to be a decent fit. It doesn't have to be reamed, but it should be a nice snug fit on the end of the part like so. And that looks good. It should be a little bit deeper than the feature. Then on top is the most important hole. This is the actual drill guide. I'll drill and ream that to the correct nominal dimension. And then on the other side, we drill and tap for a little set screw that's going to hold the part in position while we drill it. I happen to have these fancy brass-tipped set screws, but you could just use a brass screw or put a piece of brass in the hole. Now I can slide the part in there, and I'm using the outside shoulder to align it on the outside edge of the drilling jig. Sorry, my hand is blocking the action there, but I'm aligning those two surfaces with my scale. And then once that's in position, referenced to the outside of the drilling jig, I can snug down the set screw, and we are ready to go. The first step is to come in with a nominal size drill, not the reamer, the drill, and I'm just going to touch that brass, and the drill guide is going to hold that drill centered, and it's going to make a little dimple that's going to guide the smaller dimension pilot drill for the reamer, because we do want this hole to be reamed, but of course the drilling jig has to be the reamed size, not the pilot drill size, because we're doing this in the drill press, and we have to do this all in one setup. So I go through with the pilot drill size, it centered itself on the dimple, then I go through with the reamer, and now that will be correctly positioned and the correct dimension. Look how perfectly centered on the diameter that is. And also in the other direction, wait a minute, that looks off, doesn't it? Yeah, I noticed this too as soon as I had done it, and the drilling jig performed perfectly, for the record. What's actually incorrect here is the length of the connecting rod end. When I was lining up the parting blade to part off this entire thing, I did the math wrong and I parted it off a little bit too long. Hilariously, you can see me double checking this measurement with my scale, and if we stop it right here, you can see it's supposed to be 2.2 because the whole thing is 2 inches long, and I've left 200 to face off the center drill, and you can see that it's 25 thousandths over right in this shot, which is hilarious to me because in the moment I looked at that and was like, yep, that looks perfect. Let's go ahead and part this off. And yeah, well, luckily that error doesn't hurt anything. All the internal dimensions on the part are correct. And the most important dimension is the distance from the hole to the end of the piston. And that is correct. And the other important thing is that we have a good fit on this drill rod that's going to be the crank pin. We want that to be a nice close fit that runs smoothly so the engine doesn't rattle. Well, there it is so far. We've got the piston and cylinder done. Those are looking very good. It's looking very engine-y now. And we've only got a couple more parts to make. This is a really nice little quick project for anyone to build. I hope you'll give it a try. Stay tuned for the rest of this series. Thank you so much for watching. Thanks to my patrons for making all this happen, and I'll see you next time.